Okay, welcome back everybody. So, a quick review. In yesterday's sessions we saw about Laplacian eigenvalue, and we also saw the bounds, right, for the largest eigenvalue and second smallest eigenvalue, both algebraic connectivity and what will happen to my lambda 1, the largest eigenvalue, right. Under certain conditions we were seeing that, and before we stopped we were talking about the algebraic connectivity of a graph G1 given a graph G such that what is my G1, where my G1 was nothing but the graph G minus a set of k vertices, right. You delete all k vertices from G, and that is your G1. So, in this case your algebraic connectivity is going to be having this lower bound, right, AC of G minus k. So, this much we saw yesterday, and we wanted to also answer one more thing. What is the connection between algebraic connectivity and the usual vertex connectivity or edge connectivity? What would be the relation between them? Can we say something in that direction? So, one interesting result is that algebraic connectivity of the graph G is less than or equal to the vertex connectivity of G. It is bounded by the vertex connectivity, and let me just make it clear. Yeah. And it is also having a lower bound with using edge connectivity. So, AC of G is also greater than or equal to 2 times the edge connectivity of G times, if I am not wrong, 1 minus cos pi over n, right. So, this we saw in the case of path graph, right, on n vertices, because we know edge connectivity of path graph is 1, right, deleting any edge you get to disconnect the graph. So, EC of G is 1 in that case. So, therefore, we also saw that this bound attains equality for Pn, right. So, this is a lower bound. So, let me just give the notations that I am using. For VC I am just using vertex connectivity, because just to give you a feel for it I am not using the standard notation of kappa or kappa prime, right, and EC is nothing but the edge connectivity of G. Actually, you simplify it, you will get, when you solve for the expression for algebraic connectivity, you will get big. One reason is that your path graph and cycle graphs have cos in their eigenvalues. If you solve for the spectrum of Cn is nothing but, we are talking about algebraic connectivity, right. So, this is nothing but 2 minus 2 cos pi k over n, 2 pi k over n for k running between 1 to n. Okay. So, this is 2 minus, and if you look at the adjacency spectrum of Cn, it is just this quantity here, 2 cos 2 pi k by n. Okay. And this 2 minus is because you can write Laplacian spectrum of this is Laplacian spectrum as 2 times identity matrix minus the adjacency matrix. So, that is what you will get, because degree is 2, right, in Cn. So, this 2 comes from there, 2 minus this 2 value comes from there, okay. And this is going to be nothing but, without the negative sign, if you see 2 cos 2 pi k by n is nothing but spectrum of Cn, adjacency spectrum of Cn. So, not only here, but when you go along simplification, when you go for computation of algebraic connectivity, you will end up in this expression. I am not doing the expression purely because it takes more time to solve it. Simplification takes a little longer time. So, this is one thing that I wanted to cover up, and another one is about, we were talking about join of graph. In similar thing, we can also talk about disjoint union. Right. Suppose I have 2 graphs G1 and G2, I can just talk about my new graph G as with vertex set V of G as V of G1 union V of G2, and you just take the edges as it is, right. So, it is disjoint union. If we have such a thing, in case of disconnected graphs, you can easily try to get the algebraic connectivity from these components. Okay. So, in this case the algebraic connectivity is nothing but minimum over algebraic connectivity of G1 plus the number of vertices of G2, okay, comma algebraic connectivity of G2 plus V of G1. Yeah. So, these things you can just simply use the Laplacian matrix representation. From there you can easily prove the spectral value, that whatever spectral value we are looking for, that comes in this category. Okay. Okay. So, this is about our algebraic connectivity. So, today I said I promised I will do something about trees. Okay. So, we will start with a new type of matrix, and then we will also go come back to Laplacian of trees. Okay. So, I want to give one or two results in this direction, we will see about that. So, the next type of matrix what I want to talk about is for directed graphs. Okay. So, now for next half an hour or so we will think about directed graphs. So, let my G be a directed graph. So, the next matrix what we want to talk about is called as the anti-adjacency matrix. So, before we go into anti-adjacency, for a directed graph, what is going to be my adjacency matrix? Yes? You have seen any definition of adjacency matrix for directed graph before? Okay, we will take, there are actually various ways you can define. If you want to consider it as for both, if I is directed, if ij is a directed edge, then I can think about giving values for both I and j, the position ij as well as ji, right. So, if you want to maintain a kind of a symmetry, skew symmetric property, you can keep this into account, or there is also another way of defining it. So, whichever definition we are going to use, we should be specific about that. Okay. With respect to this definition, I am going to give you certain results. Okay. If you change the definition, these results may not hold. So, that fact you should be clear. Okay. So, one way of defining this adjacency matrix is, I take 1 if the edge I, if there is an edge from I to j, right. In the directed case, I mean this category. If there is an edge from I to j, then I just put 1 in which position? In ijth position. Okay, any ijth position I take it as 1 and 0 otherwise. So, now with this is a definition for adjacency. So, now we have a 0 1 matrix again, right. So, for this adjacency matrix you can see that it is no longer symmetric, right, or skew symmetric also. So, we will just have, if there is a directed edge, we just put from I to j, if there is an edge, I just say there is an edge originating from I. So, just we will take care of that part, right. So, now with this definition, what can we say about anti-adjacency? What does your intuition say? What should be anti-adjacency? Yes? Something is anti, so something should be against my A. Yes? Reverse. 0 1. That is one possibility. So, in my anti-adjacency matrix, we are just going to write this as j minus A. Wherever you have adjacency, make it as 0, and if you do not have an adjacency including diagonal entries, it will now become 1, right. So, you will have like a dense matrix having 1s and sparse zeros if you have an acyclic graph, something like that, right. Okay. So, now let us think about this. Let us consider a directed graph, and let me just show you how this kind of feels for you, and then we will go into some results in this direction. So, now we are going into a directed graph. So, let me also give you directions properly. Okay. So, this is 1, 2, 3, 4, 5. Okay. If suppose I have this graph, so the directions are clear, so the vertices are also clearly labeled. So, we get a 5 by 5 matrix. What will be the corresponding B matrix? Yes. So, I will just fill it up quickly. So, since there is an edge between 1 and 2, that is going to be 0 now, right, in the matrix. So, from 1 to 2 there is a edge, so it becomes 0, 1 to 1 no edge, so it is 1, 1 to 3 no edge, 1 to 4 also no edge, 1 to 5 also no edge. So, all this becomes 1, right. This is the matrix that we are looking for. Similarly, if you start from 2, 2 to 1 there is no edge, right, and 2 to 3 there is 2 to 2 also no edge. So, 2 to 3 there is 1, 2 to 5 there is 1, right. So, obviously, we are not looking to get an symmetric matrix, because your A is not symmetric, right. So, in that sense we will not have a symmetric matrix. So, we will have to fill this and see how this matrix is going to look like. So, if you look at oh sorry, there is no edge from 1 to 2, right. Thank you. 2 to 2 also no edge, sorry, even I have to get used to being anti-adjacency. So, and 2 to 3 there is an edge, so it becomes 0, 2 to 4 there is no edge, it is 1, and this is 0, right. Sorry about that. So, see, that's the difficulty when we keep on talking about adjacency. Now we have to think in reverse direction, so be cautious, okay. So, with 3 if you see there is no outgoing edges from 3, so it is going to be all one row for 3, and for 4 if you see 4 is nothing but you have an edge from 4 to 1, so this becomes 0, 4 to 2 there is an edge, so it becomes 0, and there is no edge between 4 to 3 and 4 to 4. And what about 5? 5 has only one outgoing edge to 3, so that would be 0, and everything else is going to be, sorry, it will be 1, and no, I was right, 0, 1, 1, right. Yeah. So, this is the matrix B that we are trying to look for. So, from here what are we going to get? Why do we have to define such an anti-adjacency, right? So, that comes as a question. So, let us look at this matrix. What can I say about the determinant of this matrix, okay, depending on a particular presence of particular edge, okay. So, that is what we will try to see next. Then next result states that this matrix, if you look at the B matrix, there is a very special property for this. If the graph has a Hamiltonian path, okay, then determinant of this matrix is going to be equal to 1 and 0 otherwise, okay. So, this matrix comes in with a very beautiful property, but for which kind of graphs, that we will see specifically. Okay. So, the theorem states that if G is, so before I go into the theorem, I want to prove one more small result which we will be using it, okay. and we will see what we are trying to do here. So, let B be a 0 1 matrix of order n by n such that my Bij is equal to 1 for every I greater than or equal to j. So, what does this mean? What kind of a graph are we looking at? Bij, we are talking about directed graphs, right. So, Bij is equal to 1 means what? There was no edge connecting I and j, right, and I greater than or equal to j is what we are trying to say, right. So, there is no directed edge in my graph if I is greater than j. Okay. So, if it was there, then we will have a 0 here, right. So, if at all there are edges, it is going to be in, like I can always find a ordering for my graph in such a way that I can rearrange the vertices in such a way that if there is an edge, it always takes from lower order to an higher order vertex, okay, I to j. It is like I am trying to say if this is there 1 to 2, 2 to 3, 2 to 5. So, every edge is going to look like this. The origin, I mean any edge originates from a smaller number to a larger number. Only then what will happen? My Bij for will become 1 for every I greater than or equal to j, right. So, keeping this in mind, we will try to talk about what will be the determinant of this matrix, such a matrix. What will be the determinant of such a matrix? So, determinant of this matrix is going to be equal to 1 if the corresponding entries, whatever we are talking about here, B12, okay, B23, I will remove this, okay, let it be there. So, B23, B34, all the above diagonal, like the diagonal, I mean the first diagonal above the main diagonal, if you look at those entries, all these entries are 0, then you will get determinant to be equal to 1. Even if there is one entry which is non-zero here, then I can say that determinant of B is going to be 0 otherwise. So, how do we prove this fact? So, what are we given? To prove this, I just need to look at the determinant of such a matrix that is given to me, right. What is given to me? I have a B matrix where I have all the entries on the diagonal and below the diagonal, or the lower triangular matrix is going to be having 1, right. Bij equal to 1 for I greater than or equal to j, right. So, so this means all these entries are 1 here for me, right. So, now what am I going to, what is my claim? B12, if suppose my B12 is 0, or let me start with non-zero case, that is easier I guess, okay. Say suppose B12 is not equal to 0, so that means what? It will be equal to 1, right. If B12 is not equal to 0, then B12 is equal to 1. That means what? Look at the first two columns, right. So, this entry 1 2 1 1 is there. If you look at the first two columns, right, if suppose this was also 1, I get two identical columns, right, of 1s. So, obviously determinant will become 0. When we have two identical columns, then we can say immediately that determinant is 0, right. So, this will imply that determinant of B is equal to 0. So, therefore, let us assume B12 is equal to 0. So, now look at this columns. Let us just rewrite this column such a way that column 1 is written as column 1 minus column 2. I am just doing a column operation, we will reduce this matrix. So, if we do the column operation, what will happen to my first column? I rewrite my first column as C1 minus C2. So, in my C2, now with this second assumption, I will have this entry to be equal to 0, right, B12 is 0 and all the other column values are 1. Right. So, if we subtract this, I get the first column now becomes 1 followed by zeros, right. So, just by this row operation I can see my first column changes to this 1 followed by zeros, and you have 0 followed by 1s, that is there, we are not disturbing any other column, right. So, now look at the determinant, expand about this first entry. Now, determinant of this matrix, I want to find the determinant, right. So, to get the determinant, expand about this first entry, what do we get? Just it is going to be the determinant of this submatrix, right. So, the same thing appears here also. So, if you look at the submatrix, if B23 is 1, then in this submatrix n minus 1 by n minus 1, we have two identical columns. So, the determinant of that submatrix becomes 0, right. So, therefore, let us assume again that this is this is 0. So, now if you again do the same operation C2 minus C3 and you write it in C2 and expand about this, if you do this recursively, you will be getting 1 into 1 into 1 product of all 1. So, determinant will become equal to 1, right, with the conditions that all these entries above the diagonal or the next element of the diagonal entry is 0, right. So, therefore, we can conclude immediately that determinant of B becomes 1 if this all these entries are 0, otherwise it becomes 0, okay, determinant is 0. Okay. So, this gives a hint to us. What does this tell you? What does this condition tell you? B12 and so on until I am going up to Bn minus 1 n. What does this tell you? There is a path like B120 means what? In my adjacency there is a edge connecting 1 and 2, right. B230 means there is an edge connecting 2 to 3, right. So, if you look at this, this gives you a Hamiltonian path connecting 1 to n. So, 1 to 2, 2 to 3, 3 to 4 and so on, you will get the Hamiltonian path, right. So, that is the corollary for this result. So, for the corollary, let us give the exact expression. Let G be a directed acyclic graph. Okay. So, the condition over here is we need acyclicity for the graph. Okay. There I did not give you any representation about being acyclic, right. Why should we have this acyclicity? If suppose there is a cycle, then what does that tell you? N? Cell n1, I did not say which edge, we are talking in general, but still if there was a cycle say 1 to n and you come back from n to 1, so that means what? Your n1 entry for I greater than j in this position, this n1 position, you will have a 0, right. But we do not want that, we want all ones in the lower triangular matrix. So, this translates to in our graph theoretic terms as G is a directed acyclic graph, right. Say with vertex set equal to 1 to n, and I am just giving this theorem completely, and B be the anti-adjacency matrix. Matrix of G, then determinant of B equal to 1 implies G has a Hamiltonian path. And determinant of B equal to 0 states otherwise, implies G has no path. Okay. So, next I think now the proof is clear for this, right. We just need to apply. Suppose there is an if and only if condition that I should state here, because of course, if G has a path, then I should prove determinant is 1, and if G has no path, then determinant is 0. So, it is kind of if and only if. So, there will be two cases. Suppose G has a Hamiltonian path, let us rearrange that path in the order of increasing vertices 1, 2, 3, 4 and so on, and by the previous theorem that we stated, we can immediately conclude that determinant is going to be equal to 1, right. Sorry. Okay. And suppose G has no Hamiltonian path, right, then I have to show that determinant is 0, right. So, to do that, what we have to do is we have to take a little bit of effort. So, suppose G has no Hamiltonian path means what? There is some vertex which is not going to be reachable, right. So, that means what? That vertex has in degree 0, right, there is no vertex edge coming into it, that is when it becomes not reachable, right, otherwise we should be able to reach it from some other vertex. So, you catch hold of that vertex and delete that vertex out of your graph, look at the rest of this, right. So, we know this has in degree 0, so what about the rest of the graph? There could be another vertex which has no in degree because the edge could have been coming from 1. So, pick out such a vertex and pick out all these, like we are now getting an algorithm where we could order the vertices in terms of in degrees. In degree 0 you pull it out, next in the remaining graph G minus V you look at that vertex which is a source vertex, we call this as a source vertex if in degree is 0. So, you pull out that. So, you look at all such vertices, you do this iteratively for I steps. Okay. Say suppose in this step I have come to I minus 1, I have removed I minus 1 source vertices. Okay. At every time in the lower level I had a source vertex, right. If suppose I am talking about an I and it is not a source vertex means what? There was some edge which was coming from I greater than or equal to j, right. If it was not a source vertex, then there is a edge coming from for some j, maybe I should just write it this way, say some vertex j whose labeling is bigger than this node. So, there is a j greater than or equal to I, so there is a reverse edge coming. So far we are trying to come down in this direction and now you are suddenly having a reverse edge which is coming from higher order vertex to lower order vertex. So, that would contradict, and by now using this previous theorem, in that case we know if there is a edge from a higher order vertex to, by higher order I mean higher labeled vertex to a lower label, then we know determinant is going to become 0 there, right. So, just by using that argument we can conclude immediately that this theorem holds. Okay. So, this is one very nice theorem that I thought I should share with you. Not only we get Hamiltonian path, okay, this matrix also gives us something more. Okay. You can also count the number of directed paths having I vertices, on I vertices. You can look at the count of directed paths. Suppose I want to have a directed path of length 3, that means length or having 3 vertices. So, we can have a count of this, okay, such that it is so easy, we will just get it from one of the coefficients. Like we did for adjacency matrix, we know each coefficient gives us some information there, right. We were talking about kth power of graph, we talked about walks, right, k walks. In similar language here, we will translate this to say that the number of directed paths on I vertices, on any I vertices, okay,